All right, today's the big day. We're going to talk about p-values and power. So we're going to have the talk. And so sometimes when a researcher and an idea have a special bond and the researcher feels very strongly about an idea, there's p-values and stuff. And can I just talk about where babies come from? This is incredibly awkward. Alrighty, let's do p-values, shall we? So p-values are this thing that comes up frequently. About every 5 or 10 years, somebody publishes a paper saying that p-values are horribly flawed and they should be banned. And people should stop using p-values for thinking about doing science, basically. And that's probably a little bit of an overreaction, some people might argue, but there are some journals that have pretty much outright banned p-values. And the main reason behind this is probably a consequence of how people are taught statistics, where we think of p-values as being this magical number that tells us whether or not we should accept or reject our null hypothesis. And so p-values are used in a null hypothesis testing framework. We've already played a little bit with thinking about a null hypothesis testing framework when we did the permutations just a couple of days ago or a week ago, whatever it was. And so, again, this null hypothesis testing framework is where you have a statement of no effect. Maybe the mean of group A is the same as the mean of group B, and then you have an alternative hypothesis where the mean of group A is different from the mean of group B. And so you have two mutually exclusive statements, and you want to use statistical analyses to decide whether or not you accept or reject your null. And so here's the first important part. Rejecting your null is not the same as saying that the alternative hypothesis is correct. All you've done is rejected the null, which has left you with accepting the alternative. So that's an important kind of philosophical thing to keep in your brain when you're thinking about p-values. And also, importantly, when you fail to reject the null hypothesis, notice I said fail to reject the null hypothesis. That is very different than saying that the null hypothesis is correct, because according to this kind of philosophy of science through falsification, you never truly can demonstrate that the null is true. You can only reject the null and accept an alternative. And so, in general, in the life sciences, we have an arbitrary threshold of 0.05 as being a level of significance. And if our p-value is equal to 0.05 or lower, then we reject the null and accept the alternative. And so we have this threshold. This threshold is an arbitrary threshold, but everyone seems to be pretty happy with it. And so let's think about why p-values might be somewhat controversial. And so the first thing is let's think really clearly about what a p-value is. And a p-value is a conditional probability. And this is the first thing that I think a lot of people don't recognize, and why p-values have kind of become somewhat controversial, in that we just think of it as a magic, or we don't, but some people do. We definitely will not. Think of it as just the probability that the null hypothesis is true, which is not actually what it is. It is a conditional probability where we have an observed value. And so when we were playing around with the t-test, for example, our observed value was that t-statistic. So we used all of our data to come up with statistics, and then we used those statistics to test hypotheses, right? We've already removed ourselves from the data, and all we have are our estimates of parameters based upon those samples. So it's the probability that we would get that observed value given that the null hypothesis is true. And this is the really important thing to keep in your mind, is that it's conditional on the null hypothesis being true. And as we'll see in a little bit, when the null hypothesis is not true, that's where p-values can sometimes be a problem. And so, again, what we did with the t-test example is we calculated this t-statistic, which was basically the deviance of our mean from 0, right? Because the t-distribution is centered at 0. And we asked, what is the probability that I would get that t-statistic if my null hypothesis were true? So it has nothing to do about the probability that my alternative is correct. It's all about what's the probability that I would observe that if my null hypothesis were true. And that seems to be fine. Okay. Sometimes people get, they don't think about it that way, but as long as we start thinking about it as a conditional probability, I think that we're on the right track. And so let's think about the ways in which we might be wrong when we're making inferences. And there are two types of errors that we might make. And these are really cleverly called a type 1 error, and wait for it, a type 2 error. Okay? These are the two types of errors that we can make. And these are, they can potentially be a problem, I suppose, but as long as we accept the fact or understand that there are two different types of errors we can make, we can keep our eyes kind of focused on the prize. And so let's think about what these two different things are. I'm going to just move myself for a minute. I'm going to remove myself from the discussion, and I'm going to just cut and paste this right out of our notes. And so a type 1 error is incorrectly rejecting the true null hypothesis. So this is where you would say, there's a significant difference between those groups, but in reality there is no true difference between those groups. It might just be a consequence of your particular sample. Again, when we're testing hypotheses, we're thinking about this population mean being different from that population mean. It's not about the difference in the samples, because if you think about it, the mean of two samples, for example, will always be different from one another, right? I mean, you're never going to have the exact same means just because it's continuous distributions. So, there's an infinite number of possible means that you could have, which means that they're always going to be different. What you want to know is how different they are. And so, again, type 1 error is incorrectly rejecting a true null hypothesis, and that's what our alpha value is. And that alpha value is our cutoff. That's that 0.05. That is the type 1 error rate. So if we're going to do these types of statistics, it's often referred to as frequentist statistics, then we have to strive to be wrong 5% of the time, because that is our arbitrary cutoff for our type 1 error rate. The second type of error can be a little bit trickier at first, but that is incorrectly retaining a false null hypothesis. Okay? And this is what people refer to when they talk about statistical power. Statistical power is your ability to detect an effect if there truly is an effect there. And it's important that we keep in mind what power is, because when we start thinking about making inferences based upon p-values, we really always are going to also want to be thinking about, well, what kind of statistical power did we actually have to observe what we observed, or to detect an effect based upon what we observed. So there are two different ways then that we can make mistakes when we're doing this type of science, right? This null hypothesis testing, deductive, frequentist approach to science. We can either incorrectly reject a true null hypothesis. We'll call that alpha. That is our threshold. That is our 0.05. But then there's the type 2 error, which is incorrectly retaining the false hypothesis. So we've failed to reject the null, but in reality, if we were the omnipotent beings in the universe, we should have rejected that null. So what goes into this beta here, right? This is going to be the thing that we're going to look at. And power itself is inversely related to beta. So power here, you'll see power equals 1 minus beta. So let's think about what goes into beta. And I'm going to pull something else here from the old handout here. So here's our beta. And then this cool little mathematical symbol here, which I kind of really dig, it is telling you that beta is proportional to all of this stuff. Okay? And you don't need to worry about this math, because this isn't the actual formal math that they use for power calculations, but this is just what it's going to be proportional to. And what do we have up here? Well, the first thing we have, let's go in order here. the first thing we have is alpha. Again, that's our level of significance. That is the cutoff where we are going to reject the null hypothesis. So again, in most cases, that cutoff is 0.05. But all it is it's our type 1 error rate, right? And we define that going in. And then next here, we have the standard error of the residual of the model. We don't have to worry about the details there, but what power is going to be based upon ultimately is some function of our significance level, where, our cutoff. Then it's going to be the variability in our sample. Okay, so how variable is our sample? If our samples are super variable, then it might be more difficult for us to detect a difference if one actually is there. Next is delta. Delta is the effect size. The effect size is how big of a difference, say, for example, with the t-test, how big of a difference was there between the means of those two groups? Okay, so that's going to be effect size. And then finally, sample size. And we know that sample size definitely affects our ability to accurately estimate parameters. And we've talked about that with the law of large numbers, for example. And so we have all 4 of these different things feeding into our ability to detect an effect if an effect is truly there. And that's what we're talking about when we talk about statistical power. So let's explore a little bit statistical power, and guess what we'll do? We're going to play in R for a little bit. Imagine that. Jim wants to play with R. We're going to play with R a little bit, and we're going to think a little bit about statistical power. So let's do it. All right, as promised, let's play a little bit with R, and let's think about statistical power. Why not? Let's do it in a brute force way. Jim loves simulating data, and everybody loves it when Jim's happy. Let's see here. So what am I going to do? I'm going to cut and paste a little code here. This is all in the code that you've had here, but what I'm going to do is I'm going to take 20 random draws from a normal distribution with a mean of 1.2 and a standard deviation of 2.4. And then I'm going to do a single sample t-test on that. So I'm going to ask whether or not the mean of, this random draw, no, unused argument, that's the problem. Right, so this would be a random draw, and I could calculate, the mean of that random draw. Okay, it's 0.886. I could take that, I could calculate the standard deviation. I could use a single sample t-test to ask whether or not that mean is significantly different from 0, and I can save the p-value. And so what I'm going to do is I'm going to do that 1,000 times. So 1,000 times, I'm going to simulate 20 random draws from this population that's 1.2 is the mean, and I'm going to test the hypothesis using a t-test. Is that mean significantly different from 0? Is the mean of my sample significantly different from 0? And I'm going to save all of those p-values. All right, so let's go ahead and do that. I'm going to set the seed, and I'm going to do it, and phew, that was a lot of work. And so now what we have is we have 1,000 p-values, right? We've just simulated it 1,000 times. Now again, it's a simulation. We are the omnipotent beings in this universe. We know that the mean is different from 0. We know that the actual true mean is 1.2. But we take a sample of 20 from that population, we run the t-test, save the p-value. Do it again, do it 1,000 times, we got 1,000 p-values. And so now let's look at the number of times our t-test was significant. And we can do that using our little logical statements. We have this object now called p-vals. And so if I were to say p-val is less than or equal to 0.05, if I were to do that, I'm going to get a bunch of trues and falses. So again, R treats trues as 1s and falses as 0s, so I can take the sum of that. Okay, so 569. So that means there was 569 times that we rejected the null and accepted the alternative. So that's how many times that we detected the difference between our sample and the hypothesized value, which is 0. And if we simply were to divide that by 1,000, since we had 1,000 simulations, there we have 0.569. So 56.9% of the time we got it right. Because in this case, again, we simulated it. We know the right answer. But we only got the right answer roughly 57% of the time. And so we could similarly do this because, you know, these simulations are neat and they're interesting, and hopefully now you look at that and you're like, oh, okay, I kind of get that. I missed a lot of the true differences based upon those 1,000 samples. And so we can use, there's a function in R, imagine that will do a power analysis for us. And for a t-test, we could type in power.t.test. Okay, so there's our function that we're going to use. And if we go ahead and we say question mark, give me a question mark. Tell me what the heck does this magical power t-test function do? It calculates power. Good. And what are the things that we're going to have to give it? We're going to have to give it our sample size, our observed delta, or the effect size, so the difference in the mean that we observe in a sample versus our hypothesized mean. So with the t-test example, it's 0. We have our standard deviation, so that's just the variability of our sample, that's our sigma. We have our significance level, which by default goes to 0.05, but that's our alpha. And then we have the power. And so what we can use this function for is we give it any 4 of these 5 things, and it will solve for the 5th thing. And so let's go ahead and do that with our power t-test. And so we would say, okay, well, we're going to have a sample of 20. That's good. A delta. Our delta is what? It's 1.2. And we know this because this is the true effect size that's up there, right? That's what this is. That is the true effect size. So our delta is 1.2. Our standard deviation is 2.4 because, again, we know that, right? And then we can think about what's our significance level. And our significance level is 0.05. And then the type, we got to give it a type because there's a couple of different types of t-test, right? Is this a 2-sample t-test? No. Is it a 1-sample t-test? Yes. And so we are going to say type is going to equal 1.sample. And we go ahead and we run that. And look at that. It's the same power that we got brute force. And so that's how we're going to interpret what power means. If we see a power of 0.56, that means that 56, based upon our sample size and the variability of our sample and our effect size, the difference in the means, and using our arbitrary threshold of 0.05, 56% of the time we're going to detect a difference. Right? And that's really close to what our simulated values were when we actually did it brute force 1,000 times. So that's what power is telling us. It's always important to think about power whenever you are accepting the null hypothesis. And this is why it's also very important to get in the habit of using the wording that you failed to reject a null hypothesis as opposed to you are accepting the null hypothesis. They're very different things because with a very small effect size, you might have very low statistical power. That doesn't mean that there isn't a difference there. There's always going to be a difference. If you had an infinite sample size, you would be able to detect an infinitely small delta. So you also have to be thinking, is it biologically relevant, or geologically, or anthropologically, whoever's watching this. You also have to always ask yourself, you know, is the difference that I'm trying to detect even relevant for the question? Right. And so there's a different way that we could do a power analysis, which is probably a good one to get in the habit of because it also does power analyses for all different types of designs. Right now we're just playing around with a simple t-test. And so there is a library called PWR, which stands for power, right? So if you install that on your computer and you load that into your workspace, we can then ask, well, what's the built-in function there? Well, the built-in function there, I'll do question mark pwr.t.test. And it, similarly to the power t-test, but now we're using pwr t-test, it does power calculations. And the arguments are the same. Sample size, your effect size, your significant level, your power, and then the type, right? And we're going to be doing a one sample t-test. So an important thing to make a mental note of, the effect size that the PWR package wants is what's called the standardized effect size. And because it's called the standardized effect size, immediately you can think, well, that's what they call it when we z-transform things. Exactly. And so what the PWR package is going to want when you give it the effect size is not the raw effect size, right? That's what the power t-test wanted. Our difference was 1.2. What the PWR test will want is this, but z-transformed. And to do that, all we have to do is divide it by the standard deviation. And so we'll go ahead and we'll say pwr.t.test. And again, n is going to equal 20. D is going to equal 1.2 divided by 2.4. So now it's a standardized effect size. It's in units of standard deviations as opposed to being in the raw units. We have our significance level, which is our alpha level. That's our type 1 error rate that we're interested in. So let's say it's 0.05, so we can be like all the other cool kids. And then our type is going to equal what? Well, this right here is a one sample t-test, and that's the argument that we would want to use. We go ahead and we run that line of code. We get the exact same answer that we got last time, with a little bit of, yeah, that's math rounding errors. But yeah, it's the same effect size, or it's the same power. And again, this 0.564 is really darn close to our brute force demonstration of power, which was just resampling 1,000 times and running all of these t-tests. And so, again, how we interpret this is we are only going to, based upon our sample and what we understand about the variation underlying that population, we're only going to detect a significant difference, 0.564, or I guess 56.4% of the time. And so, yeah, and so that's using the PWR function, and I would say go ahead and get into the habit of using the PWR function, because that's what we're going to want to use when we start doing kind of bigger models. So you're going to have to convert it into this standardized effect size. But for ease of interpretation, let's not even bother with that. Let's just keep playing with the power t-test function, because for our purposes today, that'll work totally fine. And so you can solve for pretty much anything. So based upon what we know, we could ask questions like, based upon the variation, we could ask, well, what kind of sample size would we need to detect a difference of, say, 0.8 from, let's see here, let's just write, I'll cut and paste this because this is all right there. There it is. Right? So what sample size would we need to detect a difference with a power of 0.8 of 0.25 millimeters from the grand mean, assuming that the standard deviation is 2.4? And so what we can do then is we can solve for, well, what kind of sample size are we going to need? And okay, well, we know that we want now our power. We're no longer going to ask it to solve for power. Now the one argument that we're not going to include in the function is n, is our sample size. And so we'll set the power at 0.8. Our delta is 0.25, right? That's the difference we're interested in detecting. And our standard deviation is 2.4. So there's our standard deviation. Again, we'll keep our significance level at 0.05. That's our alpha. And the type that we're going to do here is just a simple one sample t-test. And so we go ahead and we run that. And this is what kind of sample size we're going to need. And so you're going to need a lot. And it often, when people start playing with power analyses, it always makes them very sad and depressed, because somebody will say, well, why don't you run a power analysis on that and see if you have enough replicates? And it's like, well, I just worked myself to the bone getting 25 replicates and I need 725. Now I'm really sad, I'm never going to graduate. But that's just one way that we can use power analyses, right? And here again is by setting the power at 0.8, we're saying 80% of the time we want to detect a difference if there's actually a difference there. And that's going to require 725 replicates. So just based upon that, you can start to think, well, why might p-values be controversial? Well, this is a nice example of where p-values might be controversial, because as long as you have a large enough sample size, you're probably going to be able to detect a difference, right? I mean, we could go to something really ridiculous. Let's say I wanted to detect an effect size of 0.02 millimeters, right? So a really, really small effect size. You could do that with a lot of statistical power. You would just need 113,025 replicates, which might be difficult to do if you're doing something outside of the lab and outside of a petri dish. But again, this is one of the reasons why p-values have become controversial, because if you have a large enough sample size, you're always going to be able to, not always, but 80% of the time, be able to detect a significant effect. But this is also an example of where you have to use the old noggin and ask, biologically speaking, do I really care if the difference is only 0.02? So you also have to use a little bit of biological intuition in understanding the system in order to do that. And so what I want to run through next is just a series of what are called power curves. And this is a way in which, holding all else equal, we can look at how changing sample size affects our power, and how changing the variability of our sample might affect our, the number of samples we need, or whatever it might be. And so all I want to do is I'm going to plot a couple of different power curves so we can think about this. And so I'm going to just cut and paste this from the old R script that I've posted for everyone. And so first, let's think about our original thing, right? The power as a function of sample size. Let's think about delta is 1.2. That's our observed effect size. We have a sigma of 2.4. That's the variability of our sample. And then we'll keep our alpha at 0.05. And so what I'm going to do is I'm going to go from a sample size ranging from 2 to 50, right? So by doing that little line, I have now created a vector called n, which is simply going to say, okay, we're going to solve for it when we have 2 samples, 3 samples, 4 samples, all the way up to 50 samples. And we're going to run through all of these different sample sizes, and we're going to save the power at each step. So that's all I'm doing here with this loop. And again, you will never have to write loops in this class, so if this just seems opaque to you, just accept the fact that I'm going through all the possible sample sizes between 2 and 50 samples. So I'll go ahead and I'll do that. Oh, I didn't set seed. That is just bad form, Jim. Set seed. Let's set it at 2. And then I'll go ahead and I'm going to open up a new plotting window, because RStudio is just not big enough for Jim. And then I will say, I'm going to plot it. And now I have to get to it. How do I get to it? There it is. Okay. And so on the x-axis there is our sample size. And on the y-axis is our power. So when we did this original experiment where we had a sample size of 20, if we go up to here and then we scoot over to here, it's roughly 0.56, 0.57, right? As we increase our sample size, our power is going to be stronger. We're going to have more power. And so if we were to have a sample size of 40, now we're going to detect that difference, I don't know, it looks like roughly 85% of the time we're going to detect that difference. By having more samples, we've increased our statistical power, which is our ability to detect an effect. But again, our power is going to increase as a consequence of sample size. And so you are always going to increase your power as you increase sample size. And that's why people always err on the side of caution. If you're doing an experiment, more replicates is always better. And always you'll be frustrated because you'll probably never be able to have as many replicates as you truly want, but that's just life. Especially those of us that are doing kind of ecological work, there's only so many replicates in reality we can do unless we had billions of dollars and had an army of researchers collecting data for us, which we don't have. And so next, let's think about power as a function of the effect size. And so I'm going to cut and paste again. You can run through what I'm going to do. Okay? And so again, we're going to keep everything else constant, except now we're going to say, well, how big of a difference is there? And we know that our observed difference from our example was 1.2, but let's explore what if the difference was only 0.2 all the way up to if it were 3. And I'm going to try out 100 different values. So these are possible effect sizes ranging all the way from 0.2 all the way up to 3. And I'm going to just loop through, and I'm going to save the power at each one of those steps and think about how is power related to our actual effect size. So I'll go ahead and I'll plot that one out. Where is my thingy thing here? Oh no, there it is. All right, so there's our power curve. Here's our raw effect size. And then here's our power. And so again, as the effect size gets larger, our power to detect that effect size will get larger. And here we're keeping n constant. What are we keeping n at? We are keeping n at 20, right? So we're assuming we're stuck with only being able to do 20 samples from our population. And so if the effect size is really big, like 3, you can see we have incredibly high power given our the variation of our data. When we did our play example with the single sample t-test, the raw effect size was 1.2, and then we go up to here and yep, there's that 0.56 again. Okay, and so what you can importantly see when you think about the effect of effect size and power is that if you already have a pretty good idea going in that they're pretty darn different, because you can just eyeball it and be like, yeah, you probably won't need 1 billion replicates. You might be able to get away with, 20 replicates, especially if you have a really large effect size. So the bigger the difference is, the bigger the effect size, the more statistical power you're going to have, meaning that you probably don't need as many replicates to either accept or reject, or in this case, to reject the null hypothesis and accept the alternative hypothesis. And so that's the relationship between effect size and power. And then next, let's go on over here and let's think about effect size and the number of replicates. And again, these are just different ways to think about the relationship between power and other things. Here, what I'm going to do is I'm going to keep power constant. I'm going to say that I want a power of 0.8, which is pretty good power. And that's really what most people shoot for. 0.7 is okay. Anything less than 0.7, then you're in that realm of the universe where it's like, yeah, we don't really have that powerful of a design, which means that if we end up accepting the null, we have to do it with the caveat that we are not accepting the null. We are failing to reject the null, and we're failing to reject the null because we might not have that much power. And we should always get comfortable with using the language we failed to reject. Never say that we accepted the null, and try to always avoid saying there was no significant difference. That's the thing that pops up a lot in talks and in papers, is people say, oh, we did this experiment and there was no significant difference. That's not the correct way to say that. What you want to say is we failed to find a difference. It's really an important kind of philosophical thing with doing null hypothesis testing. Failure to reject is different than there is no effect. And so what are we going to do here? Where did I go? So we're going to look at what effect size we might need as a function of number of replicates or sample size. And we're going to hold power at 0.8 because that's the power we really love. We are going to hold sigma at 2.4 because that's the variability that is in our sample. And then we have alpha at 0.05 because that's going to be our magical cutoff. So I'm going to create, again, a different number of replicates from 2 to 100 replicates. I'm going to create an empty vector called effect size, because what I want to do then is I want to solve for effect size. Again, when we use that power t-test function, we give it 4 out of the 5 things, and then it will solve for the 5th. So I'm going to go ahead and I'm going to do that really quickly, and that was really quick. And then let's go ahead and look at that plot. And this is what that plot looks like. So when you have a really large effect size, you don't need that many samples, right? You don't need that many replicates. But as your effect size gets smaller and smaller, you need more and more and more samples. And you can also look at this sample size thing, and you can realize that once it gets down to here, it's almost plateaued out. I mean, you're going to be doing a heck of a lot more work, well, I guess twice as much work, if you went from a sample of 20 to a sample of 40. But that's really only going to increase your power to detect an effect size of a very, very small amount. And again, this is where we want to think about our system. Know your data, know the system that you are modeling with those data, because we might decide that, the difference between an effect size that big and that big is not biologically relevant at all, so I don't really care. Maybe I'm happy with an effect, if the effect size is that small, biologically it doesn't matter. So I'm okay with just failing to reject the null hypothesis. All right, let's look at another power curve, because power curves are fun. Let's think about power and the variability of our sample. And so again, the variability of our sample is the variability of our data tells us something about the confidence for our parameter estimate. And in this case, we're dealing with a t-test. And so it all has to do with the uncertainty around our estimate of mu. And so what I'm going to do in this, for this power curve, is I'm going to hold our effect size constant. Our effect size will be 1.2, which is what it was initially when we played around with the simulated data. I'm going to keep our sample size at 20, and I'm going to keep our alpha at 0.05. But what I'm going to explore is how does the variability of our sample affect our statistical power. So I'm going to create a vector here called sigma, and these are all of our possible variabilities ranging from 0.9 all the way up to 5.0. And then I'm going to save the power. I'm going to go through all of these 100 different possible values for sigma, and let's plot that. Okay, and you can see as you increase the variability of the sample, right, our sigma, our statistical power is going to go down, assuming that we're stuck with only 20 samples. And the effect size that we're trying to look for is 1.2. And so if we were to modify those, it would change the shape of this power curve. But what you can eyeball by looking at that is, hey, it looks like power goes down as sigma increases. And you could step back from that and say, well, that's totally consistent with, as the variability of our sample increases, our standard error is going to increase. And what is our standard error telling us? It's telling us something about the variability around our estimate of the mean. And so this should make some intuitive sense that as you have more variation, you are going to decrease your ability to detect a difference. And so that's the relationship between power and the variability of our sample. And so even though I say don't worry so much about these for loops, I mean, you could write your own little for loop and solve for, you could change alpha if you wanted to. Nobody really changes alpha because everyone's pretty happy with their type 1 error rate of 0.05. But you could play around with the variability of your sample and the number of replicates you might need. And again, when you're playing with power analyses, and if anyone ever tells you to do a power analysis, if all you're going to solve for is the number of replicates you need, you're going to be really depressed because it's always going to tell you that you probably need a ton more replicates than is possible. But also remember that what works into power is the variability of the sample, and that is what it is. But in increasing a sample size will always decrease that variability or that uncertainty around a parameter estimate. But also keep in mind what the effect size is, because you might have preliminary experiment where you fail to reject the null and the difference was really small, and then somebody says do a power analysis, and it's like, okay, now I need 20,000 replicates. But do you really need 20,000 replicates if you want to have the statistical power to detect a difference that's only this big? Because it could be that only this big doesn't really matter at all. And so those are power curves. And next, we're going to think a little bit more about, we're going to think about a different way of thinking about p-values. And let's actually play with alpha. And so what I'm going to do here is I'm going to modify sample size. And I'm going to keep delta at 1.2. Okay, so that's our effect size. I am going to keep our variability of our sample at 2.4. So that's our sigma. I'm going to say I want to solve for power at 0.8, because 0.8 is usually a number that people feel pretty good and warm and fuzzy about when they're doing power analyses. I'm not going to give a value to the significance level, because that's what I'm going to try to solve for. Okay, I'm going to try to solve for what the p's are going to be. And then I'm going to, it's a one sample t-test. So let's go ahead and we'll run through all of that. And then let's take a look at what that one looks like. Where did it go? Where did it go? There it is. All right. And so based upon all of these, if we were to do null hypothesis testing, we would have to be, if we only had a sample of 20, for example, we would have to say, well, unless we change our alpha threshold to 0.2, we're not going to be doing that well. But we would have the power to detect a difference if we decided that our alpha was going to be 0.2, which again, it's usually not. It's usually 0.05. And if you tried to get away with 0.2 being significant, you might get some eyebrows raised. And so we can let's look at this a little bit more. I'll augment this graph. And we can put here, I'm going to put a bunch of different things on here. So this first threshold here, this pink threshold, I have set at 0.07. Okay, so that would be saying I want to have a significant alpha at 0.07. And I did that just to show that the 0.05 cutoff is pretty arbitrary. Like, do we really think that, it's that different? That means if you were stuck at 0.07, if you had only had 3 more replicates, suddenly it would get to this red line, and this red line here is at 0.05. So this is the magical 0.05. And so if we kept everything else constant, we could look at this and say, I need this many samples. I don't know what that is, maybe 32, 33. And as long as I had 33 samples, I am going to have the statistical power of 0.8. So as long as I have that many samples, 80% of the time, I'm going to find significance. Whereas over here, whatever this is, maybe 20, 28-ish, maybe, I don't know. Then our significance level would have to be 0.07 in order to detect that. Again, it's entirely arbitrary, but usually people are focused on this red line here, because this red line is significance at 0.05. And as I mentioned, some fields, they don't feel really good about rejecting a null unless their p-value is below 0.01. And so that's what this blue line is here. So if it was 0.01, you'd have to have about 50 replicates. And then if you wanted to sound really fancy and say 0.001, well, that's the green line. And now you're getting way out into this neighborhood here. And so hopefully here you can also see that a potential problem with how p-values are misinterpreted is that the p-value itself is a function of your sample size, which means that if you had an enormous sample size, you're going to always be able to detect an effect. And this is why lesson number 2, you should refrain from ever using phrases like highly significant or marginally significant. Things like that don't make any sense at all. If your p-value is super duper low, it's incorrect to say that the observed effect was highly significant. Really, the only thing you can say if you have a super low p-value is, check out how low that p-value is. Boy, I had a big enough sample size, didn't I? It doesn't really mean anything. So avoid ever saying highly significant, because highly significant is very suspect and it doesn't really mean much of anything. Okay, let's go back and think about our type 1 error rate. right? And again, our type 1 error rate was the rate at which we are happy to be wrong. And so in general, we set that with our alpha at 0.05, which means that we are striving to be wrong 5% of the time. And so the first thing we can think about is what is our expectation of p-values if the null hypothesis were actually correct? Because again, p-values are a conditional probability. It's the probability you would observe that particular t-statistic if the null hypothesis were correct. So let's go ahead and simulate the null hypothesis. And so I'm going to do that because I have the power. So let's go back to R, because Jim loves playing in R. And I will cut and paste this from our little old notes that were posted. So again, I'm going to simulate something, always set the seed. And then I'm going to think about the differences. So that's going to be the difference of my sample mean from the hypothesized value, which is 0. I'm going to save my t-values, and I'm going to save my p-values. Okay, so I'm going to save all three of those things. So what I'm going to do, and I'm going to do this 10,000 times because I'm feeling very motivated. 10,000 times, I am going to take 50 draws from a standard normal, which means that the mean is 0 and the standard deviation is 1. We know that. And so I'm going to go ahead and I'm going to take this sample. So here's my sample, 50 observations from a standard normal. And then I'm going to save for the diffs, I'm going to look at the mean of y minus 0. So this is going to be how different our sampling mean is from our hypothesized value, which is 0. And again, since we simulated this data using a standard normal distribution, we know that that is actually the true correct value. And then what I'm going to do is I'm going to save the t-values. And I'm going to do this just simply by calling the t-test function, and I'm going to have it save just the statistic. Okay, so this is where we can use a list, for example. So I'm going to save our t-statistic, and then I'm going to save our p-value. And so at the end, I'm going to have 3 different vectors, which are the differences that we observed across all 10,000 of those, the t-values that we observed, and then the p-values that we observed. So I'm going to go ahead and I'm going to do that. Look at that, the computer's thinking. It took almost a second. And so the first thing, let's look at, what is our distribution of differences? Those are maybe interesting to look at. Where did my little quartz window go? There it is. Okay. There's our differences. That looks pretty nice. That is probably, one might almost argue that is probably almost t-distributed, as it were. But what's the expectation, right? We have, for the most part, the difference was 0, which we would totally expect, because that is, we know the correct answer because we did the simulations. But sometimes by chance, we got a pretty big difference in that direction, and sometimes by chance, we got a pretty big difference in that direction. Again, the null hypothesis is true in this case. And we could likewise look at our distribution of t's. And this is our t-statistic, which looks a heck of a lot like our differences, and it should look a heck of a lot like our differences, because that difference is what we're basing the t-statistic on, right? And so this is going to actually be t-distributed. And again, we're going to have some high values and we're going to have some low values. And so the shocker to a lot of people is, what is the expectation for the p-values? Again, the null hypothesis is true, and we want to know what the distribution of our p-values should be. So I will go ahead and I will plot our p-values. And normally if we were in a class session, I would let people think about this for a little bit, and people come up with ideas of what the p-value should look like. But let's look at that distribution of p-values. It's a uniform distribution. So when the null hypothesis is true, we have a uniform distribution of p-values ranging from 0 all the way up to 1. And so that's an important thing to keep in mind. If the null hypothesis is truly true, we would expect that the distribution of p-values, if we had repeatedly sampled that population, we would expect the distribution of those p-values to be uniform. And we can even go so far as to use that quantile function. And again, the quantile function is an empirical way to look across all of our data. I'm really excited about this, so I'm going to put myself back on here. That way I can look up and just be super excited about this. So we can look at the quantile of our p-values, and we can say, well, what is our quantile at the 0.025, so the 2.5th percentile, and at 0.05? And so if we do that, that's really close to what we would expect. We would expect what we observed was 0.045, so 4.5% of the time we had a p-value less than 0.05. And, you know, that's really close to the actual 5%. So our simulated data is really close to what we might expect our cutoff would be for a statistical significance. And so that's an important thing to remember when dealing with p-values, is reminding yourself that they're a conditional probability, and they are conditional on the null being correct. And which means that we have to be careful about over-interpreting what p-values actually mean if we decide to reject our null hypothesis, because they are based upon our null being true, and so maybe that's why we reject it. But we're also setting this threshold of 5% of the time we're happy being wrong, because we have to be happy to be wrong a certain percentage of the time. But again, it's that arbitrary cutoff between significance and not significance that oftentimes people get hung up on, because then it's easy to misinterpret a really low p-value as being highly significant. And there's no such thing as highly significant. There's a cutoff. We have a type 1 error rate, 0.05. You either accept or you reject the null. That's it. The magnitude of the p-values don't matter in this philosophical framework of doing deductive science. So cogitate on that for a moment, and then we're going to revisit p-values one last time, just to make sure that everybody feels happy about being really cautious about over-interpreting such things. Okay, so revisiting one last time p-values. So we might ask, okay, what's the problem? It's like we've defined what our arbitrary cutoff is. We accept the fact that we're going to be wrong 5% of the time if the null hypothesis were true, and incorrectly rejecting the null hypothesis, so committing a type 1 error. And so what's the big whoop, right? Why are p-values potentially a problem, and why are they misinterpreted? And this is a counterintuitive part of it, is that we have to keep reminding ourselves that p-values only mean something if the null hypothesis is actually true, right? That's when we got that nice uniform distribution of p-values, and we accept the fact that 5% of the time we are going to erroneously reject the null hypothesis. But things change a little bit when we start thinking about what if there actually were an effect. And so what I'm going to do is I'm going to say, let's redo the simulations that we had done. And this time let's pretend that for 15% of the populations that are out there in the universe, there actually is a difference of 0.3 standard deviations. And so for 10,000 data sets, 8,500 should not be significantly different from 0. And for 1,500 of those, we should have a significant difference between those two things, right? And again, we're assuming 100% power. This is us in a simulated universe where we are the omnipotent beings, and we know that in exactly 15% of the populations, we expect to see a difference of 0.3 standard deviations. Otherwise, what we expect to see is no difference. And so this is where the concept of power is going to become really, really important, because we can go ahead and we can calculate the power of that. So power dot t dot test. Okay, and what did I say? Delta equals 0.3. Okay, that is our effect size. We had a sample of 50 individuals. We'll say that the standard deviation is equal to 1. We'll go ahead and say that our significance level is equal to 0.05, so that's our type 1 error rate. And the type of test we're doing here again is a one sample t-test, because that's a nice easy one. So I go ahead and I do that, and here is my statistical power that I have. So here our power is roughly 0.55. And so that means that if we had a sample of 50 and we went to one of those populations where there actually truly was a difference, we're going to detect that difference 55% of the time, roughly. We also, for the remaining populations, right, we're dealing with 10,000 different populations that we've gone and sampled. For the remaining 8,500 of them, we expect to erroneously reject the null hypothesis 5% of the time. So let's walk through and see what this looks like. So I'm going to call up a quartz window, so that way I'm killing myself there. Okay, so I got a quartz window, weep, weep. And then we can go ahead and we can walk through. So where do we start? We start out with, we have 10,000 tests. So let's say that we are going to 10,000 different populations, and then we were going to ask whether or not the mean of these populations was significantly different from 0. And so we've already done the power analysis. But before that, let's think about what our data should actually look like. Yeah, let's do that. Okay. And so we know that our power is 0.55. We should detect a difference in 55% of the 1,500 that have a real effect. And then for the ones where there is no effect, so no effect in 8,500 of them, we expect to be wrong 5% of the time, right? So this is our type 1 error rate right there. And then this is telling us something about our ability to reject the null and accept the alternative. And so our power has to do with our ability to correctly reject the null hypothesis. And so now we can continue to think about that. Okay, so we have our real effect in 1,500. And we can think about, well, what could possibly happen here? So in 55% of those, we'll get a true positive. We actually will detect an effect. And in 675 of those, we'll have a false negative. We will have failed to reject the null hypothesis. And then we can go ahead and we can go down here and do the same thing for the 8,500 where there is no effect. And we know this because we are the overlords of this universe. And so 95% of the time, we expect to get a true negative. And 5% of the time, we expect to get a false positive. Again, as a frequentist, if we set our alpha at 0.05% or 0.05, we are striving to be wrong 5% of the time. So once we have that, I'm going to just take that, put that there. Okay, we can calculate the total number of positives that we have. So we have 825 positives from up here, and we have 425 positives from down there, 425. And so what does that equal? That equals 1,250. And so now we can think about what's called our false discovery rate. Like, what really is our false discovery rate? Again, if our null hypothesis were true, our false discovery rate is 0.05. That is what our alpha is. But this is a situation where the null hypothesis isn't necessarily true. And so our false discovery rate then, these are false positives down here, is going to be 425 divided by 1,250. And it's 0.34. So 34% is our false discovery rate. So even though we set our alpha at 0.05 and we were feeling very confident that we're okay being wrong 5% of the time, as soon as the null hypothesis is no longer true, now we're wrong 34% of the time. And again, it's kind of counterintuitive. It's like, well, how is that possible? Well, that is why it's possible. Right there, because we've kind of gone out and done all the calculations through here. So we can model, or we can calculate the false discovery rate using a formula which looks something like this. Let's go over here, and I'm going to just type it out here. So we can take our significance level multiplied by 1 minus the probability that we're going to detect a real effect, and divide that by all the different ways that we could get a positive or a significant p-value. And so this should look pretty familiar because this is Bayes' theorem. We're able to use Bayes' theorem because we know what our prior expectation is. We know what the probability is that there actually is a real effect, right? Which is right here, our 15%. But then we can also go down here and we can think about all the different ways that we get a positive, which again is rejecting the null, accepting the alternative. And so if I were to go ahead and do that, I could say that my FDR will get, it'll get what? So our significance, our threshold, where we're happy being, if we get a positive or if we get a significant effect, we expect to be wrong with that 5% of the time, because that's where we have set our alpha at. So 0.05 times what? Times 1 minus 0.15. And that 0.15 comes from where? It comes from here, right? That's that 0.15. And so going back now to where am I? Ugh. So we have that, so that's this, and then we divide that by all the different ways that we might get a significant effect. And so we know that our power is 0.55 roughly, and we expect to detect that significant effect 0.15, because we know that 15% of those populations, actually there is a difference. And then we go ahead and we add to that. We add to that what? We add to that 0.05 times 1 minus 0.15. And there's our 34%. Okay. And so this was kind of an easy way to do it, just looking at that and figuring out, what percentage of our significant effects are actually truly significant, which we call the false discovery rate. You can also think about it as, the expectation of false positives. Or we can stick it into this formula right here, which should look amazingly identical to Bayes' theorem. And we could even break it down where the likelihood that we detect significance erroneously is going to be 0.05. And we can think about this as an explicit likelihood statement where it's the probability of getting a significant p-value given that the null is correct. That's our alpha level. Our prior probability that the null is correct is 1 minus 0.15. And again, we expect 15% of the time for the null to be incorrect, which means that 85% of the time we expect it to be correct, and that's going to be our prior. That's what is here. And again, to remind us, the reason why we know this 0.15 is there is because this is a simulated idea. We are the omnipotent beings in the universe, and we know how many true significant results we should get. And so we have our likelihood, we have our prior, and then we have the probability of the data. And it's just simply all the different ways that we could get a significant p-value. And again, we end up with this false discovery rate, which is 0.34, which means that that is potentially a problem with p-values, obviously, because if the null is not true, you're actually potentially more probable to incorrectly reject the null. Again, totally counterintuitive, but now we've all kind of played around a little bit with Bayes' theorem, and hopefully it won't be as counterintuitive to you folks as it is to many folks on the planet. And so I want to kind of end the conversation with p-values. First, I want some takeaways. This is because this whole, both the things, main things that we talked about today are really important things to think about. We have to think about statistical power, our ability to detect something, given our sample size and the variation of our sample size. And we should always be aware of our statistical power. I know from my own personal experience that my statistical power really is always pretty crummy, because I do ecological work and I can't have 10,000 replicates. And that's okay. That means that I just have to always be very cautious about never saying there is no significant difference. Never use that phrase, ever, ever, ever. And if you really are tempted to say, boy, I really don't think there's a difference, you really need to present what your statistical power is to say that there is no difference. And you need to tell people what your effect size is. And then the second thing is, even though p-values are problematic, they're only problematic if you don't understand what they are. And hopefully after kind of going through this, you now have a much clearer idea of exactly what p-values are. Always remind yourself that they are conditional probability. They are conditional on the null being true. And then as soon as the null is not true, you can start to have a lot of false positives or false detections. And you just need to be aware of that and proceed cautiously. And so, you know, and also like phrases like highly significant and marginally significant, they don't mean anything. We have a threshold for significance. We either reject or accept the null. If your p-value is super duper low, you don't write in a paper, I enthusiastically rejected the null. No, you just rejected the null. Nobody cares about your p-value. No offense, but nobody cares about your p-value. And then as a final thought, just to make sure that the rumors about me don't persist, I am not anti-p-values at all. Yes, a lot of the work that I personally do with my own work, I put into a fully Bayesian framework, but that's just because I like the approach of doing inference to learning something about complex models, and I really don't care as much about the p-values. That said, you could go ahead on Google Scholar and look at, you know, my papers from the last 10 years, and I still report p-values frequently because sometimes they're useful. But again, always make sure that in your mind you're thinking about p-values correctly. They're a conditional probability, and that's all they are. They are one of many things that you can use to make inferences about your data. So don't get locked into it, and don't worry about it. And you know, p-value on, I suppose. So that was our introduction to p-values and power. I hope you enjoyed it as much as I enjoyed it. Remember to subscribe to the link down below and help out my sponsors. It really helps keep this channel going. Yeah, we're gonna monetize this. All right, have a good one. Bye.